Stanford University.
Let's just review for a moment the chemistry that went into the discovery of spin and the fermionic character of electrons, basically. The fermionic character implies two things, and they're actually believed to be related to each other, but they're different. One of them has to do with the spin of the electron. The spin of the electron is half spin, and that means that the spin, as far as the spin goes, if we forget about the orbital motion of the electron and so forth, the electron has two spin states corresponding to spin a half, plus a half and minus a half. The other property that qualifies the electron as a fermion is that it satisfies the Pauli exclusion principle. You can't put more than two of them into the same state. In talking about the states, spin counts. So if, for example, we ignored the spin and, for example, we talked about putting two electrons into the ground state wave function of a hydrogen atom, yes, you can do that. You can put two electrons into the lowest energy level, but only because you have the spin to soak up the Pauli exclusion principle. And so you put them in with opposite spin. If you try to put a third one in, you can't put it into the ground state. If you try to put a third one in, let's say because we're dealing with lithium, of course for helium, we can put both electrons into the ground state. In the approximation that we ignore the interactions between the electrons. In other words, in the chemist's bad approximation, incidentally, these days chemists are very sophisticated quantum physicists, really good chemists, and they're very sophisticated. But you know, the old picture of the atom, the shell model, and all those sorts of things that were simplistic, which didn't work very well, but you know, they work a little bit. You can put two electrons into the ground state of the helium atom, so the helium atom behaves as if you had two electrons both in the lowest energy state. And that's okay because they have opposite spins. If one is up, then the other is down. If one is down, the other is up. In fact, those two electrons are entangled. They're entangled in exactly the way that, well, they're entangled. One is up, the other is down, one is down, the other is up, and that's an entangled state. Once you go to lithium, you can't put another electron into the ground state, and I don't mean into the ground state of the hydrogen, of the helium atom. I mean, of course, into the ground state of the electron wave functions in the vicinity of the lithium nucleus. The lithium nucleus also has a charge, and it also has a collection of wave functions for electrons. You can put the first one into the ground state, you can put the second one into ground state, but then the third one has to go into another state. Simply no room for it. By room, I mean from the point of view of the exclusion principle. So you start filling another shell. And how many energy levels are there at the next shell? Well, we can draw our energy level picture that we drew before. Angular momentum 0, which is called the S wave, at least for the simple approximation in which the electrons don't interact. There's the ground state, and then there are excited states which still have angular momentum 0, and so forth and so on. And then there's the p waves. The p waves are angular momentum 1, or orbital angular momentum 1. P stands for something I don't know what. And the first p wave has more energy than the first S wave, and it has three states, the three possible states of orbital angular momentum 1. And then there are above that, and by accident, by the accidents, or they're not really accidents, of course, but by the funny mathematics of the Coulomb potential, the there's degeneracies, extra degeneracies that I've indicated here on the diagram, and so forth and so on. SPD, that's spectroscopic notation. At the next level, at the next angular momentum, this is L equals 0, L equals 1, L equals 2. At the next, at the D wave level, L equals 2, the lowest energy state is already up to here. 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, and so forth, 5 states for L equals 2. And that's what the pattern of energy levels looks like. Okay, so you go to the lithium atom. In the lithium atom, you put in 2 electrons into the lowest energy state. So they're both in the lowest energy S wave state. And now you have an extra electron you have to do something with. Well, you could put the extra electron upstairs at some higher energy state, but it would be unstable because it would decay by emission of a photon, which we haven't gotten to, but it would decay down to something of lower energy. What you can do is put the next electron into any one of these 4 states. Okay? Keep going. What comes after lithium? I can't remember. Beryllium. Okay, then you come to beryllium. Beryllium, you fill the lowest one, and you fill one of the next levels. But wait a minute, there's 4 electrons now, so you fill 2 of them. Okay, that's beryllium. What comes after beryllium? Boron? Boron, okay. And the one after boron? Who? Carbon. Good. Right? And if there wasn't spin at the next level, at the next atom, which is, what's the next one? What is it? Nitrogen. At the next nitrogen level, you would have to start filling up these up here. But that's not the way it works. The spectroscopy and everything we know about it is consistent with putting the 5th, is it the 5th electron? 1, 2, whatever. The next one fits in again into one of these levels, and that works until you've gotten to neon? Neon. Okay? In neon, there are 8 electrons in this first excited energy level here. Why are there 8? Well, one for each orbital state, but you also have the spin degree of freedom. So there are 8 states that can be occupied here. And then beyond neon, I don't remember my chemistry, whatever. Sodium. Who? Sodium? Yeah. Right. Sodium is the next metal. And right, you have to put one of them up here. And you know the story. I mean, you know the story as well as I do. Valence electrons and so forth. Sodium looks sort of like hydrogen, and so does lithium, because it has one extra electron in the outermost electron orbit, and so forth. I didn't want to do chemistry tonight. I just wanted to remind you that 2 things seem to go together: the exclusion principle and the spin-a-half. Now, could you have, here's an interesting question, could you have particles which were spin-a-half but didn't have an exclusion principle? You could put a spin-a-half. Oh, before I talk about that, let's talk about photons. Do photons have an exclusion principle? Photons most certainly do not have an exclusion principle. And in fact, classical electromagnetic waves are typically waves in which many quanta photons are all in the same state. That's what makes them classical, that they have a very, very large amplitude, a very, very large number of photons all in the same state. And so photons most certainly don't have an exclusion principle. In fact, it's almost the opposite. There's a tendency for them to want to be in the same state, but of course photons don't want anything. but they do tend to congregate into the same state, whereas fermions, the half-spin particles, can't be in the same state. So you might ask, could there be a particle of half-spin which doesn't satisfy the Pauli exclusion principle? Or could there be a particle of integer spin? Photon is an integer spin particle, spin 1, or even spin 0. Could there be one of those which does satisfy the Pauli exclusion principle? And the interesting fact is that they go together. Half integer spin, that doesn't necessarily mean spin 1 half. It could be spin 3 halves, spin 5 halves, spin 7 halves. Those half spin objects always satisfy the exclusion principle, and the spin integer particles never satisfy the exclusion principle.
Is that a theoretical result?
That's a theoretical result.
From something more fundamental?
It can be derived from the principles of quantum field theory. We won't get to that. But I'll show you a little demonstration tonight. All you need is a belt to understand some aspects of it. There's some interesting topological aspects of it, which we'll try to get to. This is...
Yeah, it's not a theorem in non-relativistic quantum mechanics.
No, it's not.
And
That's correct. That's correct. It's not a theorem.
And it's also not true in 1 or 2 dimensions, spatial dimensions.
Right. That's true.
For the bosonic states, is there a maximum number of quanta you can put into a given state?
In the bosonic case? No. No. Nope. And there's a strong tendency for them to want to get into the same state. Okay, and we'll try to get to that. All right, this business is a tale of 2 minus signs, 2 distinct, different minus signs, one having to do with spin and one having to do with what I'll call exchange. But before we talk a little more about the relationship between the half spin and the exclusion principle, let's talk about the Pauli exclusion principle itself, which has a deeper meaning than just saying you can't put 2 particles into the same state. It's a statement about the nature of wave functions of multi-particle systems. If I have a multi-particle system, and now when I say wave functions, let's for the moment forget the spin, and I'll come back to the spin and tell you what to do about it, but let's forget about spin for a moment and say that the coordinates of the particles that we're talking about are called x sub I. I does not stand for x, y, and z. It stands for particle 1, particle 2, particle 3, and so forth. So x1 represents particle 1, and so forth. And x could be x, y, or z. We're gonna suppress the 3 components of position, just call them x, but I represents the particle. And then a basis of state vectors is to give the positions of all of the particles. Let's write x1, x2, x3. Just as for one particle, we can label a complete set of states by just prescribing the position of the particle. For a system of particles, we can just label all of the positions, and those are an orthonormal family of states, a complete set of states. And just as for one particle, we can define the wave function to be the inner product, whatever the state vector happens to be. This is an abstract state. It's an abstract state of the system of n particles, some number of particles. And the wave function itself is the inner product of the state vector with the specific state vectors, let's call it xn. That is called psi of x1 through xn. What do you do with it? You square it. Well, you don't square it. You multiply it by its complex conjugate. And when you've multiplied it by its complex conjugate, the result is a probability. It's the probability to find the first particle at x1, the second particle at x2, the third particle at x3, and so forth. So this is multi-particle quantum mechanics in a nutshell. Now, let's suppose that what we're talking about is identical particles. In other words, particles of exactly the same species, electrons, or whatever they happen to be, ignoring spin for the moment. Particles which are identical, we have to ask the question, we talked about it last time, we have to ask the question of whether a particle 1 at position 1 and particle 2 at position 2, is it the same state or is it a different state than particle 2 at position 1 and particle 1 at position 2? In other words, that's the blue electron at position x1. That's the red electron at position 2. But electrons don't have colors. They're identical, indistinguishable. And so it's an interesting question to ask, should this state be counted as exactly the same as the state with a red electron at x1 and a blue electron at x2? As far as we know from all experiments, as well as from all theory, from quantum field theory, relativistic quantum mechanics, the rule is that these are the same state. Okay? So, for example, let's just take two particles. That tells us, for example, that the state that I would label x1, x2, blue particle at position x1, red particle at position x2, is exactly the same as red particle at position x2, sorry, blue, which one was number 1? Number 1 is blue. Blue particle at x2, red particle at x1. In other words, there is no difference between a state with two particles are two particles, to say it that way. On the other hand, in quantum mechanics, the physics of a state, the physical properties of a state, don't depend on one particular parameter. They don't depend on the overall phase in front of the state vector. In terms of wave functions, the overall phase in front of the wave function never plays into anything that is physically measurable. That's because all probabilities and all expectation values involve psi times psi star. So it's conceivable that really the right relationship is not that x1, x2 is equal to x2, x1, but something a little bit looser than that. x1, x2 is a phase, e to the I phi. Some numerical number, which is a pure phase. Let's write it e to the I phi of some sort. Well, phi is just a fixed number. It's possible that when you interchange two particles, that the wave function should pick up a phase. On the other hand, supposing you do it twice. Supposing you interchange x1 and x2, and you say, when I interchange x1 and x2, the wave function should get multiplied by the phase e to the I phi, and then you do it again. You interchange them again. You get back to the same place. You get back to the same place. You get back to the same state that you started with. In other words, when you interchange twice, you really do have to come back to the same thing. There's no other possibility. So the general guess would be that e to the I phi here is either plus or minus 1. It's an operation. When you do it twice, you get 1. But there are two possibilities. There are two sensible possibilities. Well, you might say only one sensible possibility, but then you'd be leaving out half the particles in the world. Equals plus. Those are called bosons. particles which satisfy that property, that when you interchange any two of them, and in fact it could be a multi-particle state where you just take any two and interchange them, if the state is exactly the same, then they're called bosons. So bosons satisfy the property that the wave function or the state vector, when you interchange any two of them, stays the same. Fermions are the case with a minus sign. Okay, so when you switch two fermions, identical fermions, the state vector changes sign, keeping in mind that the change of sign is itself not observable. It's not an observable thing because the probability distributions, expectation values, everything of interest involves psi times psi star. All right, so if the state vectors change in this way, then the same must be true of the wave functions. For example, let's take x1, x2 psi. That's by definition psi of x1 and x2. Whoops, not so good. The wave function of particle 1 and particle 2. On the other hand, is x2, x1. That's equal to psi of x2, x1. In other words, the two wave functions are related to each other but just by switching the arguments. But now, if the state vectors themselves have this property that they either change sign or don't change sign, then the wave functions must have the same property. So this becomes a property of wave functions. And let's write it down. If you have a wave function for fermions, for a system of fermions, x1, and now let's just do it for two particles, and then I'll tell you what to do for many particles. The rule is, for fermions, it must be equal to minus what you would get if you interchange the particles. If you interchange the particles, the wave function changes sign for fermions. What about bosons? For bosons, no change of sign. x1, x2 equals plus. Okay, let's think about some states and see what sense we can make out of this. Supposing I have, let's take the case of bosons first. The case of bosons is a little simpler. No change of sign. Let's suppose we have two bosons in two different states. Well, one state could be, let's again forgetting spin. One state could correspond to some particular wave. It doesn't have to be an atom, incidentally. It could just be any system. But let's take some of these atomic states here. Okay. This wave function, or the wave function associated with this state here, could be called psi 0, let's call it. 0 because it has 0 angular momentum and because it's the lowest energy state. All right, so we're going to put particle 1 into that state. So the wave function for particle 1 would be psi 0 of x1. Let's put the next particle in some other state. It could have the same angular momentum or a different angular momentum, but let's make it a different state. Let's make it a different state. Well, let's first do the case where we put two particles into the same state. No, let's put two particles into the same state. Then the state vector would be psi 0 of x2. Particle 1 in the state psi 0, particle 2 in the state psi 0. Does this satisfy the rule for fermions? Does it satisfy the rule for bosons? Well, this structure here is obviously unchanged if you interchange 1 and 2. It doesn't matter which order you multiply wave functions. Wave functions are just have numerical values. They're not operators, they commute. Okay, so this wave function here, two particles in the same state, that's symmetric. The word is symmetric. Symmetric on the interchange of the two arguments of the wave function. It does not change sign. So if such a wave function makes any sense, it makes sense only for bosons. Okay. For fermions, this is not possible because this does not satisfy the rule for fermions. Okay, let's try another state. Okay, and another way of saying it is you can only put bosons into the same state, two bosons into the same state. Okay, let's take one particle and put it into psi 0, and the other particle put it into another state which I'll call psi 1. Okay. What happens if I interchange 1 and 2? Not 0 and 1, but what happens if I interchange x1 and x2? This will become psi 0 of x2, psi 1 of x1. In general, if these are two different wave functions, the left side and the right side will neither be equal to each other nor equal to their negative. Just product of two functions. Sine of x1 times a hyperbolic moose of x2. Okay? That has no symmetry whatever. It doesn't change sign or it doesn't stay the same. So this is not a possible wave function for either fermions or bosons. Does that mean you can't put one particle into one state and another particle into another state? Not quite. Let me now take a state which is made by taking both of these combinations here and adding them. This is a wave function, perfectly good wave function. It's a superposition of particle 1 being in psi 0, particle 2 being in psi 1, and the opposite, particle 2 being in psi, but both of them have a particle in psi 0 and a particle in psi 1. They both satisfy the criteria that there's a particle in psi 1 and a particle in psi 2. So both states have been filled. But what about this? What happens to this if I interchange 1 and 2? Nothing. It stays the same. Okay? So this is a perfectly good candidate for a boson system. Two particles in the same, no, a particle in state 1, in state 0, and a particle in state 1. And here's how you build it. What about fermions? Can you create a state with a fermion in this state and this state? Yes, all you have to do is put a minus sign here. Okay, can you check? Does that change sign when you interchange x1 and x2? Sure it does. This one goes over to here, this one goes over to here, and the whole thing just changes sign. So yes, you can put, in both cases, you can put a particle into state 1 and a particle into state 0. What you can't do for fermions is put two particles in the same state and two particles, or for bosons, you can. Okay. In particular, let's take the special case of exactly this, where psi 1 and psi 0 are the same state. It's just a special case in which instead of taking two different states, I take the same state. Okay, so two possibilities, psi 0 of x1, psi 1 of x2, plus psi 0 of x2, psi 1 of x1, boson, fermion wave function. Now let's take the case, as I said, where both wave functions are the same. Well, this just gives me twice the original wave function. All right, it may not be normalized correctly. We may have to normalize it appropriately, but it gives us twice the original wave function, and it's not 0. Nothing wrong with it. Again, it's two bosons in the same state. Perfectly good. But the fermionic construction here gives us what? 0. So again, we can't make a state in which two fermions are in the same state. The same rule continues if you have multi-particle states. If you have multi-particle states, any number of particles, then the wave function is a function of many variables. And it has the property that for bosons, if you take any two of them and switch them, the wave function does not change sign. For fermions, if you take any two of them and switch them, it does change sign. Again, what happens if you switch twice so that you come back to the same configuration? Clearly, in both cases, nothing happens. Right. So the process of double swap is nothing at all, is trivial. It doesn't do anything, as you would expect, but the odd thing is that the process of single swap, which you might have thought does nothing, changes the sign of the wave function for fermions. Okay, so that's, if you like, the basis, the mathematical basis, the mathematical set of rules that goes with the Pauli exclusion principle, that you can't put two particles into the same state for fermions. Now, what about when there's spin? Well, when there's spin, the easiest way to think about it is just to add another, for each particle, instead of saying the wave function is only a function of position, think of it as a function of position and spin. All right? So in that way, you can think of the wave function as a function of position and, let's say, whether it's up or down. We could choose sigma z here, z component of spin. This wave function has the following meaning. Its magnitude, its squared magnitude, is the probability to find the particle at position x with spin either up or down, depending on whether you put in sigma z equals 1 or sigma z equals -1. So it's a function of a continuous variable and a discrete variable plus or minus 1. And it represents the amplitude, the probability amplitude for the particle to have a certain location with a spin either up or down. Once you know that, then you say, okay, the wave function for many particles one here stands for the particle, not whether it's x, y, or z, x2, sigma 2, and so forth and so on. This representing the wave function for a particle to be at position 1 with spin sigma 1, position 2 with spin sigma 2, and so forth and so on. And now the rule is exactly the same, that if you take all of the stuff that's associated with particle 1, that's both x and sigma, and you take the things which are associated with particle 2 and switch them, for bosons, nothing happens. For fermions, the spin change, the sign changes. All right, but what it boils down to is exactly what we said in the first place. You simply can't put two particles into the same state, including spin. Including the spin, if they're fermions, you can if they're bosons. Okay, any questions about that so far? Yeah.
You know what this sort of reminds me of a little bit is that you've got a bunch of things and you kind of interchange them for fermions and you get a minus sign. Sort of this makes me think about the permutation, the minus sign that goes with permutations.
These are the representations of the permutation group.
Okay, so that comes into this.
Yeah.
Okay.
Yeah, switching the particles is a permutation, And what happens to them under permutation, a plus or minus sign defines a representation of the permutation group. Right, this is very definitely has to do with permutations. So it not only reminds you of it, it is it. Yeah.
When you wrote down, when you had particle 1 as psi 0 and particle 2 as psi 1, you wrote that as the product. Why not the sum?
Oh no, the sum of two wave functions is a wave function for one particle. It's simply the superposition of, to build a theory of two particles, the state vectors are the tensor products, are in a tensor product space of the wave functions that depend on two variables. And no, you wouldn't want to add them. Adding them would correspond to putting a single particle into a superposition of states. Right. Yeah. So right, there's two things you can do if you have two wave functions. You can take a single particle and put it in the sum of the two of them, or you can take two particles and put one in one and one in the other. And for one in one and one in the other, the rule would be the product. Yeah.
So here we have two particles, and swapping the particles gives interference effects.
Gives what?
Interference effects.
Well, so far I haven't. It certainly does give interference effects, but we haven't talked about interference yet. I may talk a little bit about interference later and the effects of these things.
So the fact that you got 0 when you calculated that means that the amplitude squared is going to be 0. So there's no probability for it to be like that, which is destructive interference.
Indeed. That's right. You could say the Pauli exclusion. All right, fine. You could say the Pauli exclusion principle is a manifestation of a funny kind of interference where if you put the two particles in the same state and switch them, they interfere. Good. So yes, so it is a kind of interference phenomenon. You're right. Yeah.
Is this the same logic Pauli used to derive the exclusion principle?
Yes. Yeah. Of course, when Pauli was doing it, he wasn't deriving the principle. It was an empirical fact. And he was, if you like, interpreting the principle, finding a mathematical framework in which the principle would be correct. Later on, of course, once there was a relativistic theory of particles, and this rule here became part of the logic, inescapable logic, then there was a derivation of the equivalence principle, the exclusion principle. He was trying at first to describe an empirical fact. Of course, once he realized this, that there was such a nice mathematics to it, undoubtedly he started looking for deeper reasons for the mathematics. And eventually he found them. Dirac and Einstein were the people who really built this, and Bose, but and Fermi, I suppose. I don't know if, for the life of me, Fermi was a very, very great physicist who did many things. Excuse me, Giorgio, I don't want to insult the Italians, but there he is. But I really don't understand what he had to do with any of this. Okay. Giorgio, your homework is to find out what Fermi did.
So for a single particle, essentially swapping two indistinguishable paths gives interference. Is there some connection between those two things?
Between what and what?
Between swapping particles giving interference and swapping paths giving interference.
Well, what you're doing is you have two paths for two particles. This path where one goes this way, one goes this way, and another path where they cross over. They sort of wind up the same way. And with bosons, they add. With fermions, they can cancel. So it is connected with interference. But I didn't want to do that now. There is an interesting interference experiment that you can do. But let's come to it later. Okay, that's the tail. That's one minus sign. Now, this sign will come back at us many, many times, but there's another minus sign that has to do not with exchange. This is the minus sign that has to do with exchange of particles. This is the minus sign that has to do with spin, but it has to do with rotation about an axis by 2 pi. Okay. Rotation by 2 pi is another process that you might expect does nothing, right? You might expect rotation by 2 pi is a mathematical process that you can imagine in your head, but if you take a system and imagine mathematically rotating it by 2 pi, not grabbing it and rotating it, but mathematically just performing a transformation which rotates it by 2 pi, you've done nothing to it. You've done nothing to it because a rotation by 2 pi is just the identity rotation. It's the same as the identity rotation, you think, or I thought. You may not think. I did think at one time in my life. So you might say, okay, let's now consider a wave function for a particle, one particle now. Psi of x. And now let's rotate our frame of reference. Or, better yet, rotate the particle. I'm only interested in the spin right now. All right, so there's a wave function of the particle. It might depend both on position and spins. Yeah, so we can put some spin in here. It depends on whatever it depends on, but in particular it depends on the spin. And now we rotate by some angle. What happens when you rotate a state with a given angular momentum by an angle? Well, you have an idea?
Are we rotating this
About any axis, whatever. An exterior axis, right? An exterior axis. The particle could be located. The particle could be located at the origin.
So this is essentially orbital angular momentum, then, is that right?
No, it's whatever angular momentum it has. Everything, right? Everything, including the spin, rotation, and so forth.
Do we orient it with respect to the spin in your rotation?
We don't know what the spin is. The spin, no, it could be, yes, it could be rotation about the z-axis. Remember, the spin doesn't have to be along the z-axis. It could be along the x-axis, could be along the y-axis, could be along any axis.
So the axis of its angular momentum could be rotated.
Yes, if its angular momentum is pointing in some direction and you rotate about some other axis, the angular momentum could rotate about that axis. But by the time, here's the angular momentum, here's the axis we're rotating about, and we rotate. But by the time we come back by 2 pi, we come back to the same place. So you might expect that if you rotate the wave function, remember, rotations are unitary transformations. Let's just call it R. R for rotation. We rotate the wave function by an angle theta. We rotate the wave function by an angle of theta. We get something new in general. But if we rotate by 2 pi, then presumably we should get the same thing back. The probability should be unchanged. The probability for spin should be unchanged. The probability for anything should be unchanged. Because all we did was an imaginary process where we, in our heads, rotated about 2 pi. And so we should come back to the same thing. But wait, the same issue occurs as occurred over here for exchanging particles. If all we require is that probabilities and expectation values don't change, then it's possible that when you rotate by 2 pi, you pick up a phase. Again, could be a plus or minus 1. It could be a plus or minus 1. Might even be some weird phase, but there's the possibility that a phase could be in here. Now, how does the phase that occurs there depend on the angular momentum of the state, the total angular momentum of the state? The angular momentum, remember what the angular momentum is. The angular momentum, let's write the total angular momentum now, that includes the spin and the orbital angular momentum. It's usually called J. J is the generator of rotations. That means when it acts on a state, when J acts on a state, it sort of differentiates it with respect to an angle. In particular, let's say J, the Z component of J, the Z component of the angular momentum, that effectively takes the state, and just like momentum differentiates a state with respect to position, angular momentum differentiates it with respect to angle. So let's write that out. That's in fact correct. Minus I, the derivative of the state with respect to some rotation angle. If we imagine rotating the state by a little bit or any amount, then acting with J does the same thing as differentiating with respect to theta. That's what a momentum does. That's what an angular momentum does with respect to an angle. And this angle would be about the z-axis. We're rotating about the z-axis, and that's generated by the generator Jz. Okay. Let's suppose that the angular momentum about the z-axis had a definite value, the eigenvalue equation. Then we would write that this is equal to m. M would be the eigenvalue of Jz. It would just be m times psi. Whoops. M times psi. We can think of this, we can think of psi as a function or as a vector, it doesn't matter. What's the solution of this equation? The solution is that psi of theta. In other words, the psi that you get when you rotate by angle theta is what? E to the I m theta psi of 0. This is just the equation that says a derivative of something is equal to m times the something. And that would be the solution of it. Okay. Remember what were the eigenvalues that we discovered were possible for the z component of angular momentum when we analyzed the commutation relations? Remember we did that? We found two kinds of things. One had integer spectrum and the other had half integer spectrum. That was just a mathematical exercise using the commutation relations, just abstract algebra, and just fiddling with it, following Dirac as far as Dirac followed his nose, playing with commutators. We found out that m could only be integers or half integers. What if m is a half integer and you rotate by 2 pi? In other words, supposing you rotate all the ways around the axis so that theta is 2 pi, then we get the fact that e to the I 2 pi m times psi again. E to the 2 pi m is 1 if m is an integer, but it's minus 1 if m is a half integer. So evidently, these representations or these multiplets that have half integer spin have the odd property that when you rotate around by 2 pi, the wave function changes sign. Those are the only two possibilities. The spectrum is either integer spin or half integer spin. It's true in 2 dimensions, it's different. But in 3 dimensions, the spin is either the integer type or the half integer type, which means that when you rotate around a full 2 pi, either the wave function changes sign or it doesn't. Whether it changes sign or it doesn't simply depends on what kind of particle you're talking about. Incidentally, if you rotate by 4 pi, it comes back to itself. 4 pi is 2 pi squared. No, 4 pi is 2 pi, you know what I mean. Yeah. Now there's a demonstration that goes with this which really does reflect some of the mathematics. In the mathematics, it seems that rotating by 2 pi is not the identity for fermions. It's not the identity. It doesn't change expectation values. It doesn't change probabilities, but it is not the identity operation. In a little while tonight, I'll show you how actually the rotation by 2 pi is an observable effect. It is an observable effect, and therefore, I think we have to say that in quantum mechanics, rotation by 2 pi is not the same as no rotation at all. There's something going on in the mathematics of rotations which says you have to rotate by 4 pi for the mathematical operator to give you just 1. All right? Now, there's a famous trick. I believe it was due to my friend, I don't know who first invented it. It was Dirac who certainly first invented it, who understood it. But long after Dirac, a circus performer by the name of Gerard 't Hooft, who's a Dutch circus performer, invented a trick to demonstrate the fact that rotations by 2 pi are not the identity, and rotations by 4 pi are the identity. I love to do this so much that I'm going to do it, and you're supposed to do it with a cup of coffee. All right, so here's the trick. Here's this. I'm going to rotate by 2 pi. Okay, now don't worry, I'm not going to go rotate this way. I'm going to rotate this way. Okay? That is not the identity. Let me tell you, I'm quite certain that's not the identity. Let me rotate another 2 pi. That's the identity. Now, there is mathematics to that. Yeah. Gerard. I think he did discover it. Now, what I think Dirac understood was a little bit different. Oh, it was the same thing. I think his picture was you take a sphere and you put it in a box. And you connect the sphere by ropes, you know, here's your sphere, here's your box, and you have ropes connecting it, strings connecting it to the box in all possible directions, okay? First, think two-dimensionally. What happens if you rotate the ball by 2 pi? You get a tangle, right? You get a tangle. You can't undo that tangle. Rotate by 4 pi, you still can't undo it in 2 dimensions. In 3 dimensions, what is true is if you rotate by 2 pi, you get a tangle. That tangle is basically the tangle of my arm after I go 2 pi. But then if you rotate again 4 pi, you can untangle. So this is a theorem. It's a theorem about of the topology of the rotation group. It's a theorem that no matter how complicated the set of connections with the walls of the box, if you rotate by 2 pi, you cannot disengage the strings back to the original configuration. If you rotate by 4 pi, you can. So it really is a mathematical fact about rotations that rotations do not bring you back to the same configuration after you rotate by 2 pi, unless you specifically say, I'm only going to study the kind of wave functions which do come back. Then you're dealing with bosons, and the other possibility is the kind of wave functions that change sign.
But if you, with the sphere and the connected strings, rotating twice around the same axis,
Yeah.
you can untangle.
Yeah. I just showed you.
Wait, but it looked like you a little different, like you were working in the 4th dimension or something.
No, 3rd dimension.
It looked like you were working in an extra dimension.
Yeah, well, you're also working in an extra dimension here. It's time. You're rotating it with time, but that's not the point. Yeah, you are in a sense working in a. you're following a path in the space of rotations. And a path in the space of rotations can be unwound for 4 pi. It can't be unwound for 2 pi. So you know, any topologist will recognize this as a feature okay, so that is the difference between the half-spin representations and the integer spin representations, their behavior under 2 pi rotations. Fermions get a minus sign, bosons don't get a minus sign. So we have an interesting situation. As I said, a tale of 2 minus signs. Fermions, the wave function for 2 fermions, now this is for 2 fermions, changes sign when you swap them. The wave function for a single fermion changes sign when you rotate it by 2 pi. Wouldn't it be interesting if there was some mathematical connection between rotation by 2 pi and exchange? And there is such a connection. Even theoretical physicists tend not to know this for some reason. I don't know why. Mathematicians were stunned by it when I showed them. They didn't know it. Most theoretical physicists don't know it. It was a discovery of a friend of mine by the name of David Finkelstein, who was one of the unsung heroes of physics. Whether he's a famous physicist or not depends on what crowd of people you're asking. If you're asking an older generation of very, very famous physicists, like Roger Penrose and people like that, they certainly know who David Finkelstein is. If you ask the man in the street, they never heard of David Finkelstein. They say, my butcher was named David Finkelstein, my butcher in the Bronx. But David Finkelstein was one of the great unsung heroes of theoretical physics. He figured this out, and I'm going to show you what he figured out. It's really fascinating. Here's my belt. Now, I'm going to do something with the belt, and then we're going to talk about what it is I did. I hope I can do it. I think I can do it. All right, we're going to do a double twist of my belt, okay? This is done easily with a rubber band, but if I did it with a rubber band, you couldn't see it from here. All right, notice if I hold it this way, you see an exchange. You see the 2 bottoms of the belt here having been exchanged. On the other hand, if I turn it around, you see there's a rotation by 2 pi. The belt has been twisted by 2 pi. Okay? A rotation by 2 pi together with an exchange gives you nothing at all, gives you an untwisted belt. So somehow in the mathematics of, I'll draw the picture. I think I can draw what the picture. It's just in case you couldn't see it on my belt. I'm just drawing what was going on my belt. Let's see. It looks something like this. Will I ever get to this if I twist my belt? I don't think so. Okay, what do I have to do to make it a legal twist of my belt? What I have to do is twist it by 2 pi. Then it's a legal twist of the belt. That's what I showed you by twisting it. And that's a legal twist of the belt, meaning to say you can twist the belt that way. And if you do, and you pull it apart, you just get the topologically trivial belt like that. So this is equivalent to this. And what it's telling us is a deep topological connection between the process of exchanging. If I have, this could be thought of in the following way. that if I have two particles and I do two processes on them, the first process is I take one of them and rotate it by 2 pi. And the other process, is I switch two of them. They cancel each other out. So that means, quite apart from whether they're fermions or bosons, I appreciate this is not an obvious connection. I'm telling you this because a lot of people think this really is at the root of the spin statistics theorem. I do. That the deep topological connection between rotation and exchange may very well be what's going on. And what it says is that whatever doing nothing is like doing a rotation by 2 pi and an exchange, both together. Okay, this is not the way Pauli proved the spin statistics theorem.
Question?
Yeah.
So this one doesn't have anything to do with the topology of the belt, but has to do with how the belt sits in space and its interaction in space.
Yeah, but particles sit in space too, you know,
Right.
and time. This can be thought of as a history with time going up. This can be thought of as a history. If you want to think of it as history, you imagine that a pair of particles was created over here. You had no particles and you created a pair. Same thing over here. You had no particles and you created a pair. So by the time you've gotten to this level over here, you have 4 particles. 1, 2, 3, 4, right? You have 4 particles, each being thought of as a cross-section through the belt. Okay? Now what you're doing is you're taking one of the particles and rotating it by 2 pi. And at the same time, you're taking the other 2 particles and switching them. And what it's saying is the switching of these 2 particles, whatever sign you may or may not get, must cancel the sign that you get for rotating one of them. Okay, this is something deep that's never been completely explored. Yeah.
Is there a connection between this and the idea of a Mobius strip where if you switch to 2 sides, the top and bottom,
Yeah, it's connected with that. It's connected with that. Right. But a path, a process, yeah, well, okay, so let's see what the process is. The process is you start with nothing. You see, this kind of logic only makes sense in a theory where particles can be created. It would not make sense in a theory where particles were eternal. Yes?
I've seen another funny argument about exchanging, going by 2 pi by having 2 particles, basically taking a symmetric role in the exchange. And I didn't really like this argument, but I wonder what you think of it. Okay? So when we exchange them, one goes 1 pi, the other goes the other pi, but we actually cause them to spin, okay, by pi. So we need to rotate them by pi in order to get the identity back.
You rotate each one by pi.
Yeah, so we get 2 pi because there's this one and then there's this one, so that's 2 pi. And then you rotate
It may be the same mathematical fact.
180 degrees here, 180 degrees there, and now they're both pointing in the same direction if they were pointing in the same direction, opposite directions if they were pointing opposite.
Well, it's a little bit different because what we want to study is a rotation by 2 pi, not 2 rotations by pi, but that sounds like they might be connected. Okay, what's the process that's reflected here? You start with nothing. Now, in a theory where particles can be created out of nothing, quantum field theory is a theory where particles can be created. But there are other kinds of theories where particles can also be created. Just creating certain kinds of excitations in condensed matter physics can create particles. But in a theory where particles can be created, you start with no particles. So your starting point is no particles. Blank blackboard. And then over here and over here, basically you're creating a particle and an antiparticle. Over here and over here, you're creating a particle and an antiparticle. If these particles were charged and you create them out of nothing, obviously they must have opposite charge, but that's not the important thing here. You do whatever it takes in your theory to create a pair of particles out of nothing. You have to put in energy for sure, but you do it. And now you're left with 4 particles. 1, 2, 3, 4. Let's see. Particle, antiparticle, particle, antiparticle. And then with time, as time goes on, at the same time that you rotate one of these by 2 pi, at the same time, you interchange these two. So I suppose if this is a plus charge and this is a minus charge, this better be a minus charge and this better be a plus charge, because you're going to interchange the 2 minus charges. You get some phase from rotating this particle, and you get some phase from interchanging these two. But as you can see, topologically, this is completely equivalent to just creating a single pair of particles and annihilating them. And for that, there is no phase. So whatever phase you got from exchanging must cancel against the phase that you got from rotation. I like this argument a lot. I think this can be turned into a real argument. But I've never actually seen it done. So it's amazing. What's very surprising is how few physicists actually know this argument. Anyway, it does show that there is a connection between rotations and exchanges. And a relation of the right kind. Okay, so that was the tail. This is a suggestive argument that I've never seen turned into a rigorous argument. It's the closest I can do to a proof of the spin statistics theorem without going through the complexities of, you see, what some of us noticed a long time ago, in the 60s and so forth, and that's when David did this. It's a rather famous paper, but not famous enough. What people noticed is that the spin statistics was more general than just relativistic Lorentz invariant quantum field theory, which is what Pauli proved it for. You could prove it for all kinds of particles that you could make things called solitons or things called solitary waves. A solitary wave is just a lump of field, that doesn't have to be in a relativistic field theory. Any kind of theory where you can manipulate the fields and create lumps, this would apply to the lumps. That was kind of noticed by a few people, particularly Finkelstein and Rubinstein and a few others. And it was Finkelstein who said, look, that's the criterion, that you can create particles. If you can create and annihilate particles, then they must satisfy this rule, whether or not it's relativistic quantum field theory. So that's why it's even true for lumps of stuff in condensed matter physics. certain kinds of particles which are just excitations lumped. It's true for magnetic monopoles. It's true for all kinds of things where Pauli's argument really doesn't apply directly. So presumably this is what is at the root. What's that?
So solitons can be created and
Yeah.
annihilated?
Yeah. Yeah. If you have a field theory, let's say some sort of scalar field, it doesn't matter what it is, any kind of set of fields. And let's suppose, okay, so here's what you can do. Let's take some lump-like field configuration. The field is 0 everywhere except in some little lump region over here. And in this lump region, and when I say a field, it could be a set of fields. It doesn't have to be a single field. But in the region over here, the field has some non-zero value. And also it has a shape and a structure. So let's put some lumps, blue lumps over here. And let's put some black lumps on the other side. Now take another configuration of exactly the same kind.
Is there a physical realization of lump?
Oh, absolutely. There's all kinds of physical realizations of lumps. Yeah, nuclei are lumps. Yeah. And in some theories, nuclei are lumps of this type. Yeah, there's what are called Fermion theories of the nucleus, and yeah, there's lots and lots. And my magnetic monopoles are like this. And in modern quantum field theories, almost all particles can be expressed this way. So yeah, this is common. Okay, here's another similar particle. It's got a lump, similar lump over here and over here. And a couple of black lumps over here and over here. Now I've chosen to draw two lump configurations which happen to be mirror images of each other. I can do that. I can make two mirror images. Call this one a particle, call this one an antiparticle if you like. Now start bringing them together. Notice that when you bring them together, the fields will exactly match. Why? Because the field over here is the same as the field over here. The field in a little bit over here is the same. So now imagine bringing them together. And what happens as you bring them together? As you bring them together, you can get to a situation, where's my red pen? You can get to a situation, for example, you will get to a situation halfway through where the black lumps have annihilated each other and the blue lumps are still there. I didn't draw them very well. And you keep squeezing it, and because the fields always match on the mirror, you can just bring these fields together and undo them. Again, you can see an example of this with a belt. Somebody come up and hold the other end of the belt for me. Okay. All right, you grab it over here, a little closer to me. Other hand, no, grab the end too. Be the mirror image of me, okay? No, rotate. Right, okay, there's a lump over here, and there's a lump at Art's end. Now, let's push the lumps together. I don't know if we're gonna be able to do this. Because, well, you can see what happens. They're going to undo each other because they match in the middle, right? So grab it over here. Okay. By the time we brought the lumps almost, no, hold it. But I'll do all the twisting. There's a lump over here and there's a lump over here. But if I keep pushing them together, we can just unwind it. That's what's going on here. this is a three-dimensional or two-dimensional version of the same thing. So given a theory with lumps, the lump and its mirror image can always annihilate each other. Okay, so if you start with nothing, oh, and of course you can go in the other direction. You can take your empty space and coil full of lumps. Create a pair of lumps. Right. So you can create this pair of lumps, you can create another pair of lumps over here, and you can rotate one of them by 2 pi, interchange the others, and be certain from the topological theorem that, that it's the same as doing nothing. All right, so the spin statistics theorem says that lumps come in 2 types. Those which, when you rotate them, the wave function changes sign, and those where the wave function doesn't change sign. Those are fermions and bosons. Half spin together always goes together with the properties, or the integer versus half integer spin always goes together with the properties under interchange of the particles. That's the theory of bosons and fermions.
The other way I heard it described was that for spin a half, if you rotate it by 180 degrees, the intrinsic spin only goes 90 degrees. So if you go 2 pi, it goes to -1.
No. If you go to 2 pi, it goes to -1.
Right?
Yeah.
And so if you go 4 pi, you get
Oh,
back to 1.
yeah. Yeah, no, that's exactly this. That's exactly this over here. If you rotate by a little bit, you pick up an e to the I theta, e to the m theta. If m is an integer,
M is a half, and it basically gives you half the phase effect.
yeah, exactly. That's right. That's correct. And that's what half integer spin means. That it rotates with half the phase so that a full rotation doesn't bring you back to the same thing. Okay, question. An interesting question is whether the fact that when electrons are rotated by 2 pi, that the phase changes, is that observable? Is there a way to observe that? And you might think, well, no, that's completely unobservable, because rotating by 2 pi, if it only changes the sign of a wave function doesn't matter. But not quite. I'm going to show you how, and this has been carried out experimentally. I'm going to give you a sort of purist version of an experiment, which in a not quite pure way actually was carried out successfully. All right, let's start with an experiment where you wouldn't see anything, where you would not see an effect. You take an electron. Here's the electron. It has a spin. We're not going to worry, well, oh yeah, we're going to worry, yeah, we are going to worry about the, yeah, right here. Here's the electron. It's going to go through some slits, do some interesting interference experiment of some kind. It's going to go through some slits. And before it goes into the slits, from this side over here, we're going to put it in the cavity. The cavity is going to have a magnetic field. Okay? The magnetic field, what does a magnetic field do? It latches on to the spin the same way a magnetic field latches onto a compass needle. All right? Latches onto it, holds it still. And then we're going to take that box and slowly rotate it by 2 pi. And then we're going to let the electron out of the box and create an interference pattern over here. We're going to compare that with the same experiment in which, instead of slowly rotating the electron, we're not going to slowly rotate it. That's all. We're going to do exactly the same experiment. In one case, a very slow, we're going to take our time. This is going to take a long time. It's going to take 1,000 years to do this experiment, or maybe 1,000,000 years. In the first 10 to the 15th seconds or whatever it is, we'll spend setting it up by either rotating this electron or not rotating this electron, and then we'll look at the interference pattern over here.
Why is it so important to do it so slowly? Or why is it important to do it so slowly?
You want to, if you drag it fast, it won't hold on to it, that's all. Yeah. Okay, so that's the experiment, and the result will be that the interference pattern in no way remembers the whether it was rotated by 2 pi. Okay. But now we'll do a different experiment. We'll take the electron, and electrons are like photons. You can have beam splitters. Beam splitters will take an electron and split the wave function of it's one electron, not 2 electrons. One electron, and the beam splitter splits its wave function so that the part of the wave function goes one way, part of the wave function goes the other way. Again, this is not 2 electrons, it's just 2 parts of the probability. So the first thing we do is we send the electron through a beam splitter. And 2 wave packets come out. I will say over and over again, these are not 2 electrons. This is a superposition of states in which the electron went this way and the electron went this way. Okay, now we're going to go slow motion for a while. Both wave packets are fed into a box, into 2 different boxes. And in the box, again, there's a magnet and a magnetic field. Okay, so what do we have? We have a superposition of states in which an electron is here, an electron is here, and in this one, the electron spin is kept parallel to a magnetic field, and in this one, it's kept parallel to a magnetic field. But now I rotate one of them and not the other, slowly. Okay, slowly until I'm finished rotating it. One of them is rotated, the other has not rotated. If rotation did nothing, rotation by 2 pi that is, if it did nothing, you'll say, well, nothing, I mean, you know, we may have done this thing, but nothing, there's no effect of it. This rotation by 2 pi brings it back to the same configuration. But no, rotation by 2 pi, we have a wave function. We have a wave function which is psi 1 of x plus psi 2 of x. Psi 1 of x is the wave function in this box. Psi 2 of x is the wave function in this box. But after rotating, we get psi 1 of x minus psi 2 of x. If this is the wave function that comes out of here with a minus sign, and it passes through these 2 slits, the interference pattern will be quite different than if you had plus. You can see why. What will come out of here will be a certain wave function. What comes out of here will be a certain wave function. And if you add them or subtract them, you get quite different, either destructive interference or constructive interference. So this experiment shows that under certain conditions, you really can detect the rotation by 2 pi by an interference experiment. Yeah.
I'm not sure what's being rotated there, since you said there's 1 electron and 2 wave functions.
One electron, which is in a superposition of states. It's either in one box or in the other box. You don't know which. And don't look, because if you look, you ruin the experiment.
Well, what is this electron? I'm thinking of the electron as moving. Is it moving?
No, you've captured it, and you've captured it for a while. You went into a box.
So they're now cavity electrons.
Yeah, they're cavity electrons in a box.
But there's only 1 electron.
There's only one.
It's in both boxes.
No, well, is it in both boxes or is it in one box or the other? It's in a wave function which is a superposition of the 2. If you open the boxes and look, you will find only 1 electron. Okay? You'll either find the electron in one box or the other box. If you don't, and of course, if you open the box and look, you affect the experiment in a way which destroys any interference pattern.
The point is, if you repeat this experiment many times, you will build up a pattern of constructive interference or of destructive interference.
Yeah, but you can really do just one experiment. With the minus sign here, you might get a node in the wave function. A node means a 0, let's say right at the symmetry point over here.
You can't find that without seeing that the events never occur.
Let me finish.
Okay.
If the wave function comes out minus, then for sure you will not detect an electron over here. So if you do detect an electron over here, it means that there must have been a plus sign. So it's quite observable. This is not exactly the way the experiment was done. I'll tell you how the experiment was done. The experiment was done a little bit differently. The electron beam was split again, and it was sent through some cylinders with magnetic field in them along here. Now, it was arranged so that after the beam splitting, the electrons were polarized in a direction perpendicular to the magnetic field. Do you remember what happens if a spin is in a magnetic field and the spin is perpendicular to the magnetic field? It precesses. So if you make the cavity just exactly long enough and the magnetic field just right and the velocity of the electrons correct, you can arrange so that the electron executes one 2-pi rotation. I guess in one of them you don't put the magnetic field, I guess. One of them you don't put the magnetic field, the other one you do put the magnetic field. So one branch of the wave function executes a 2-pi rotation. The other branch of the wave function does not execute a 2-pi rotation, depending on whether you turn on or not the magnetic fields.
How do you determine which, if you only have one electron, how do you determine the path of that one electron?
You don't. That's always the point of quantum mechanics. Anything that you do to determine the path ruins the experiment.
Yeah, but what's your source of electrons?
What you do is you go over here and you look at the interference pattern that happens.
What is your source of electrons? What does it look like? Is it
A hot wire.
just a hot wire? So electrons go everywhere.
Yeah, but you can, with appropriate electric and magnetic.
Few electrons, that only one is going to go through.
What's that?
And you have so few electrons, that only one goes through the time.
Yeah, one at a time. One at a time, absolutely. Yeah.
So, pardon my ignorance here, but what do you mean by a branch of a wave function?
Psi1 plus Psi2 or some. The branch of the wave function just means the wave packet that goes one way or the other way.
So, but it's got the same wave function? Just
No, one of them is non-zero here and 0 here. The other one is non-zero here and 0 here.
before it, in the other case over there, you're just sending electrons in, and one of them is doing something to the wave function, the other one isn't.
Yeah, but you're arranging a wave function initially. The wave function is set up by the beam splitter so that it is, let's call it psi1 of x plus psi2 of x. And psi1 of x is non-zero in the vicinity of this cavity, and psi2 of x is non-zero in the vicinity of this cavity.
I guess I'm wondering how you get psi1 and psi2. In other words, I think if you got the electron, you've got psi.
Yeah.
So is psi1 equal to psi2? Is psi1 equal to 1/2 psi, or?
No.
No?
Psi1, for example, is some function which looks like that. Psi2 is some function which looks like that. They're in different places.
This is kind of the property you can think of as the property of the splitter.
Property of what?
Of the splitter.
Yeah. So you have, okay, so you have over here, you have electron coming in, and it hits something. It hits something, let's say some target over here. The target is a particular kind of target which splits the beam into two packets. It splits the beam into two packets. So a wave coming in just splits into two pieces. They're charged particles, so we can manipulate them with electric and magnetic fields. And we take this piece of the wave function and send it through here, this piece of the wave function and send it through here. If it wasn't for these magnets, this would just be the two-slit experiment. This would essentially be the two-slit experiment. It's just we have some fancy splits, fancy slits. The fancy slits are equipped with some magnetic fields which may or may not be turned on. If the magnetic field is turned on here, even though what it does is takes the state and just rotates it by 2 pi, it takes you from constructive to destructive interference over here.
I mean, couldn't you tell which slit it came through by seeing which tube it came out of?
If you look, you destroy the interference. If you look, you destroy the interference. Anything after it hits here? No, it just makes a dot there. That's all. It doesn't tell you which.
Let's say you could tell by if you took the center point which one of the two slits it came.
No, you can't.
No.
It spreads out.
Are the
diffraction.
tubes after the slits or before the slits?
You better go back to the two-slit experiment. Go back to the two-slit experiment because this is exactly the same as the two-slit experiment. If you like, you can think of the two-slit experiment. You can do it for electrons and for photons. Wave function comes. It either goes through this hole or this hole, but you don't look. At this hole, you equip with a little cylinder here, and this hole you equip with a little cylinder. And in one of them, you do or you don't put a magnetic field through it. So if you like, a coherent beam of electrons comes. Coherent beam of wave-like electrons comes. It's just a wave. Comes in. Some part of the wave goes through here. Some part of the wave goes through here. And the wave reassembles itself, or we detect an electron over here. If there's no magnetic field in here and here, then the wave function is symmetric up and down, and we expect that the amplitude at the center here is going to be the sum of the two of them, and it's going to be particularly large.
It may be helpful. You drew the circles on the left-hand side. If you draw the circles on the right-hand side, you get diffraction. So you get circles around each of the slits. And
Just
then
a wave going through.
And then they interfere.
Yeah, this is, right, this is,
And if they interfere constructively, then you get this reinforcement at the middle.
waves go through the slits, and they spread out.
So you don't know which, when you get a dot on the screen, you don't know which way it went.
No, you don't know which way it went, and if you do know which way it went, you destroy the interference path.
And that relies on the diameter of the tubes being on the order of the wavelength of the
What's
electron.
that?
The diameter of the tube has to be on the order of the wavelength of the electron. It has to be very,
The diameter of this?
yeah, it has to be very small
Yeah.
in order to get that diffraction. Right?
Yeah, this is not really the way you would do it, but if you wanted to do it by a conventional two-slit, yes, you'd have to make it small.
So if you did this experiment with photons and had a way to rotate them 2 pi, the two patterns would be the same.
That's right. That's right. If you did the same thing, if you had a way to rotate the polarization of the photon, there's ways to do it, what would come out here would not be sensitive to whether you rotated by 2 pi or not.
It's easier to do with photons than with electrons.
Probably. I never thought about it, but
What, you said there was a slight cheat in this somewhere, right? Didn't you say that? They sort of cheated or something?
well, the purest version of it is you want to take that electron and very, very slowly rotate it so that you know that nothing else is going on. Here, it's not slow. The electron goes through quickly, and but still, it's the same phenomenon. It's the same phenomenon. No, it's, the slowness just makes sure that there aren't other things going on, jiggling and,
If it was a really long pipe, even though the electron's moving fast, if it was a really long pipe in a weak magnetic field,
Yeah.
the rotation would be very slow.
Okay, it's illegitimate. It's measuring the same effect. It's measuring the same effect. It's measuring the effect of rotation by 2 pi on a fermion, right? Yeah, this is all a special case of a phenomenon called a Berry phase. But a berry phase, like a strawberry phase or a raspberry phase or a Michaelberry phase. Actually, the experiment was first proposed by Aharonov and myself a long time ago, but yeah.
So when the experiment was done, was it considered a big deal, or was it like, yep, that's
Yeah.
what we thought?
When the theory was proposed, it was considered a big deal. Everybody, by that point, enough of these kind of things had been done, everybody knew it would have to work. But, you know, right. It was, yeah, it was considered something surprising that people had thought that under no circumstances was there any empirical signature of a rotation by 2 pi. So it was interesting. Yeah.
In the experiment where you have the beam splitter, don't you have to recombine after?
Yes,
you-
of course. Yeah. Yeah. Well, the wave function, I'm not sure what recombines mean. The wave function goes through and comes out and spreads out here. And this one spreads out from here. And it creates an interference pattern by the classical interference phenomenon.
So the splits themselves recombine.
What's that?
The splits themselves recombine.
Yeah. It is. It really is just a 2-slit experiment, except with something inserted in near one of the slits to do something to the electron. And as I said, these things are always destroyed if there's any, you know, little Maxwell demon watching what's going on that records what goes on. Yeah.
Do you happen to remember if you and Aronoff thought of this idea before or after the so-called Aronoff-Bohm effect?
Oh, it was after. Oh, yeah. No, it was after, definitely. Yeah. 1967, I forget, the Aharonov-Bohm effect was the late 50s? I can't remember. Yeah.
Yeah, a long time.
Yeah. No, no. Right.
What is this effect?
The Aharonov-Bohm effect?
It's another funny interference experiment.
Is it the bomb tester thing? Have you ever heard of that? This is sort of,
Oh, yeah, the vitamin.
oh yeah, that's
Yeah,
it.
yeah, yeah, yeah. Yeah, that's a very beautiful idea. Yeah. Right. Doesn't really have to do with bombs.
Yeah, right. That gets your attention though.
Yeah, it gets your attention, right. Okay, that's, yeah.
Is it, in some sense, is this expected because it isn't just that the probability of not being able to combine fermions is 0, they actually cannot be combined into one state.
It's only one fermion. You're not combining 2 fermions.
No, I mean more generally, talk about putting 2 electrons into the same state, which can't be done.
Yeah, but this doesn't have anything to do with that because there's only one electron.
Right.
Yeah. Now, the question is, could you do the same thing exchanging electrons? Yeah, you could do the same thing exchanging electrons. It's more complicated, harder to visualize. You start with a pair of electrons. Now you literally start with a pair of electrons. And what you do is okay, here's some possibilities. You take, these things are wonderful. They can be anything you want them to be. There's 2 electrons, okay? Now, what you're going to do is you're going to split the beam of 2 electrons. That means you're going to create a state which is a superposition of 2 electrons over here and 2 electrons over here. It's only 2 electrons, no 4 electrons. It's not 1 electron, it's not 4 electrons. It's 2 electrons, but either the 2 electrons are here or the 2 electrons are here. And now, if the 2 electrons are here, there's an apparatus which exchanges them. somebody, a field grabs onto them and exchanges them. If they're down here, no such thing happens. Or perhaps we forget to switch on the thing which exchanges them. So the other possibility is no exchange on either branch. So we split the beam of 2 electrons so that we have either 2 electrons here or 2 electrons here. If they're here, we exchange them. If they're here, we don't exchange them. And then we bring them back together again and interfere them and see what comes out of this thing afterwards. Question is, do you get the same thing or something different if you decide to exchange these 2 guys here or if you don't? Does the exchange, which after all does nothing to them, right? I mean, if the state doesn't care about which electron is which. And of course the answer is that the experiment for fermions will detect the fact that you exchange the 2 particles. The experiment for bosons will not. Now, what would happen? All right, here's another experiment. We split the pair here or a pair here. If the pair is here, we interchange them. If the pair is down here, we rotate by 2 pi.
So you would think they'd cancel.
Right. They will. Yeah, they will. They will cancel. The 2 effects will cancel. Right. That's the... to my knowledge, nobody has ever done that experiment. I have a feeling that one is, at the moment, probably beyond the...
So does that in any way challenge the idea that the 2 electrons are indistinguishable?
What? No. Well, it is what it is. Indistinguishable means that if you interchange them, it changes sign. That's what it means. It means the quantum notion of indistinguishable is more subtle than the classical. As usual, that's the sort of thing it means, right? Now, of course, what's going on here, in both of these cases, in the case of the single electron, where you rotate one part of the world and you don't rotate the other part, of course, that is not truly a rotation by 2 pi. A true rotation by 2 pi is the whole world has to rotate. If the whole world rotates, then you don't see anything. Okay. But all experiments that you ever do are compartmentalized into, so it's.
The whole universe is a fermion.
No, it still will not be visible. Yeah, so the reason this is detectable is because you've rotated one part of the universe relative to another. Right. But still, you do detect the fact that rotations by 2 pi cause a change in sign. So, and that was surprising at the time. Okay. Yeah, it's surprising today, right? Okay, we're done for tonight.
For more, please visit us at stanford.edu.